So it seems that in my last video, I wasn't entirely clear about how to prove the gambler's ruin probability of reaching C, their success, before reaching ruin, reaching 0. So just to be extra clear here, let's let x sub n be a simple random walk with some initial fortune A and probability P of winning each bet, right? So then if we define some function SB to be our probability of reaching success before we reach ruin, like we do here, when we start at that fortune B, for any B, greater than or equal to 0 and less than or equal to C, then we just want to find S of A, right? Because that's our initial fortune in this problem. And to do that, what we'll do is we'll solve a general formula here. And I'll have you notice that by definition, right, S0 is 0. Since if we start with $0, we can never win. We've already hit ruined. And then if SC is 1, right? Because if we start with C dollars, we've already won. So now we just want to find the probability from B between 1 and C minus 1. So the magic here is that it's easy to understand what happens on the first bet, right? Since we'll either lose $1 with probability P or win $1 with probability Q, where Q is just, 1 minus P. And that leads to this guy on the bottom here that you guys see S of B, that function. Now, if we win the first bet, right, we will have fortune B plus 1. And then we get to start over, quote unquote, in our quest to reach C before reaching 0. Except this time we're starting with our fortune B plus 1 instead of B. So after winning this first bet, our chance of reaching C before reaching 0 is now S of B plus 1. And the same thing is true for our losing, right? If we lost that single turn, but now it's S of B minus 1. Now, obviously, we still don't know what either of these guys are. We don't know what S of B plus 1 or S of B minus 1 is. But this connection is going to help us out in a moment since, right, we had C plus 1 unknowns, our S function over 0 to C. And now we have C plus 1 equations. So we'll be able to solve this system of equations pretty simply, right? First, though, let's just do some classic sequence stuff and rewrite, everything to be a bit more digestible. So notice that this first guy is just possible because, P plus 1 minus P equals 1. So I'm not changing anything. I'm just multiplying by 1 on the left-hand side. Then all I do now is, I rearrange this so I have 1 minus P on the left-hand side, all those terms, and then P on the right-hand side. And then finally, if I just do this, I get this nice ratio. This is just algebra. But the key idea here is that we're looking at S of B plus 1 minus S of B. So already, you might see, okay, some telescoping stuff's going on. And if you want, you can pause the video and try to work out what I'm going to do next. But the goal is just to find a series that represents S of B. So to do that, we're going to deal with induction. So if you recall from our last slide, right, we know S of 0 equals 0. So our base case, we can just go, okay, what's B of 1? What happens when B equals 1? So we know that based on our last slide, S of 2 minus S of 1 will equal 1 minus P divided by P times S of 1. And that's because we can drop the S0 since it's equal to 0, right? Now, if B is 2, then we know that S of 3 minus S of 2 is our probability ratio times S of 2 minus S of 1. But wait a minute, right? That whole guy, S of 2 minus S of 1, we just proved was our ratio times S of 1. And then we know that we have, 1 minus P over P squared times S of 1. So you can prove rigorously by induction that we have S of B plus 1 minus S of B equals this guy right here, where our ratio is to the power of B times S of 1. If we just say S of B is this sum on the left-hand side here, right? We can do that because that sum is telescoping. Remember my hint I gave you earlier. So telescoping means that I'm subtracting and then since I'm adding them back together, it will end up simplifying to S of B. And then I can just plug in my 1 minus P over P to the power of I times S of 1, which was my thing that I just proved for all the B's. And because this is a nice geometric sum, bear with me here, we're almost done. We have this guy here, right? Where to start, we'll just do our special case where P is 1/2. which is special just because our ratio from that sum will become 1. And as such, our sum will simplify to become b times s of 1. And then we can just use a geometric series for our second part there, right? The bottom half of this case by case when p is not equal to 1/2. And that follows directly from our sum on the last slide. Now, we can just plug in c here, right? And then you're like, okay, why are we plugging in c? Like, why aren't we plugging in a? But this allows us to get rid of s of 1. And that's because s of c is 1, as we established earlier. So to find s of 1, we just need to write it in terms of, everything else here. So that's what we do in this step right here, where I move my s of 1 out, and then I get 1 over c when I'm p equals 1/2, and then I get, the reciprocal of that other ratio that we were multiplying by s of 1. So all we do is we plug in a, right, to s of b, just to be clear here. And then now that we know what s of 1 is, we just multiply that in each case. And then we're going to get this final guy at the bottom here. And yeah, we're done. It was that easy. And sorry if there wasn't enough intuition in this video. I just felt the need to justify my last video with full rigor. So this proof is also in full in quite a few places. You can find it in Rosenthal's fantastic probability book. And I think Columbia has a good resource. So yeah, thanks for listening.